There is a moment, approximately 4 days after leaving Earth's orbit, when the protection ends. Not the oxygen, not the food, not the water. Those problems are solved. Engineers have been solving them for 60 years, and they are solved well enough that a crew can survive in a pressurized capsule for months without running out of anything they need to breathe or eat or drink. What ends is the shield. Earth's magnetic field, the invisible planet-sized force generated by the churning liquid iron at the planet's core, extends approximately 40,000 miles into space in the direction facing the Sun. It deflects charged particles. It turns away the constant high-energy bombardment streaming from the Sun and from sources far more distant and far more violent than the Sun. It is the reason life exists on this planet. The reason the surface of Earth is not a sterile, irradiated wasteland identical to the surface of Mars. 4 days out from Earth, you leave that shield behind. And what is waiting on the other side of it is not the serene, star-filled emptiness that science fiction has spent a century making look inviting. What is waiting is an environment so comprehensively hostile to human biology that every moment spent inside it is a moment the universe is trying to kill you. Not dramatically, not with explosions or monsters or the disasters that make good cinema, quietly, persistently, at the cellular level, in ways you cannot feel until the damage has already been done and the timeline has already shortened. The reason no one has yet survived deep space, the reason we have been a spacefaring civilization for 60 years and have not placed a single human being beyond the moon's orbit, is not political. It is not financial. It is not a failure of will or imagination or ambition. It is biology. The specific, fragile, extraordinarily Earth-adapted biology of a species that evolved inside a magnetic field, under an atmosphere, within a gravity well, in conditions that the rest of the universe almost never provides. The moment you leave those conditions behind, the universe begins the work of taking you apart. And the closer you look at exactly how it does that, the specific mechanisms, the cellular cascades, the neurological deterioration, the genetic damage, the cardiovascular collapse, the clearer it becomes that the barrier between humanity and the stars is not a rocket equation or a funding gap. It is us, what we are made of, and what the cosmos does to what we are made of when we take it somewhere it was never designed to go. This is that story. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. To understand why deep space is so profoundly hostile to human biology, we first need to understand the environment that human biology evolved in, and how radically different that environment is from what lies beyond Earth's protective embrace. For approximately 3.8 billion years, life on Earth has existed inside a layered system of protection so effective, so comprehensive, that we barely register its existence. At the outermost layer sits Earth's magnetosphere, a vast invisible magnetic bubble generated by the convection of liquid iron in Earth's outer core, extending roughly 65,000 kilometers above the surface on the sunward side and stretching millions of kilometers in the anti-sunward direction as the solar wind shapes it into a comet-like tail. The magnetosphere deflects the vast majority of charged particles streaming from the sun and from distant cosmic sources, routing them around the planet rather than allowing them to penetrate to the surface. Inside the magnetosphere, Earth's atmosphere provides a second layer of defense. The 100 kilometers of gas above the surface, particularly the stratospheric ozone layer at 15 to 35 kilometers altitude, absorbs ultraviolet radiation from the sun, filtering out the wavelengths most damaging to biological molecules. The column of air above any point on Earth's surface provides shielding roughly equivalent to 10 meters of water, a substantial barrier against the secondary particle showers produced when cosmic rays interact with atmospheric molecules. Together, these layers reduce the radiation dose at Earth's surface to approximately 2.4 millisieverts per year, a unit, the sievert, that measures the biological effect of ionizing radiation, accounting for the type of radiation and the tissue receiving it. At this background level, accumulated across a human lifetime, the statistical increase in cancer risk is real but modest. The evolutionary machinery of DNA repair, refined over billions of years of exposure to background radiation, manages the damage adequately. Venture beyond the magnetosphere, and both layers of protection vanish simultaneously. The International Space Station orbits at an altitude of roughly 400 kilometers, still within the magnetosphere, still receiving partial protection from Earth's magnetic field. Astronauts aboard the ISS accumulate radiation doses of approximately 150 to 200 millisieverts per year, 60 to 80 times the surface background rate, but still within the range that medical science can characterize, monitor, and partially mitigate through mission duration limits and shielding. A crewed mission to Mars changes the equation entirely. The journey, using current propulsion technology, takes approximately 6 to 9 months in each direction, with a surface stay of approximately 18 months while waiting for the orbital mechanics to align for the return trip. A total mission duration of approximately 3 years. For the transit phases of the journey, the crew would be completely outside the magnetosphere, exposed to the full intensity of the deep space radiation environment. That environment has 2 primary components. Solar energetic particles, or SEPs, are high-energy charged particles as primarily protons and electrons, ejected from the Sun during solar flare events and coronal mass ejections. These events can occur without warning and deliver intense, short-duration radiation doses. During a major solar particle event, an unshielded astronaut in deep space could receive a lethal radiation dose within hours. Protection against SEPs is achievable. A small, heavily shielded storm shelter within the spacecraft can provide adequate protection for the duration of most events, which typically last from hours to a few days. Galactic cosmic rays, or GCRs, are the second component, and they are the problem that no current shielding technology can solve. GCRs are high-energy charged particles, primarily protons and heavier atomic nuclei, originating outside the solar system, accelerated by supernova shockwaves, active galactic nuclei, and other extreme astrophysical phenomena across the galaxy. They arrive at Earth from all directions, continuously, at energies ranging from millions to billions to trillions of electron volts. The most energetic GCR particles travel at velocities so close to the speed of light that their relativistic mass is orders of magnitude greater than their rest mass. What makes GCRs so difficult to shield against is precisely their energy. Unlike SEPs, which are relatively low-energy particles that can be stopped by modest amounts of material, GCRs penetrate almost anything. When a high-energy GCR particle strikes a shield, whether made of aluminum, polyethylene, water, or any other material, it initiates a cascade of secondary particles: neutrons, gamma rays, pions, muons, and more charged particles. Depending on the shielding material and thickness, this secondary shower can actually deliver a higher biological dose than the primary particle would have alone. Thin shielding makes the problem worse. Thicker shielding helps, but the mass penalty, the additional weight required to achieve meaningful GCR reduction, quickly becomes prohibitive for spacecraft design. NASA's own analyses of the Mars mission radiation environment estimate that a crew would accumulate approximately 300 to 900 millisieverts of GCR dose during the round trip, depending on the solar cycle phase, mission trajectory, and spacecraft design. To put this in perspective, the current NASA lifetime occupational limit for astronauts is 600 millisieverts, a limit set to keep the excess lifetime risk of fatal cancer below 3%. A single Mars mission for some crew members would approach or exceed that lifetime limit in a single voyage. And that was the picture before recent research revealed something even more alarming, a finding so unexpected that it required an entirely new framework for thinking about deep space survival. Radiation does not just cause cancer, it reshapes the brain. In August 2018, a research team led by Charles Limmerly at the University of California, Irvine, published findings in the journal Scientific Reports demonstrating that exposure to GCR-like radiation in mouse models produced significant, persistent changes in brain structure and function. The radiation triggered chronic neuroinflammation, disrupted the normal branching patterns of neurons in the prefrontal cortex and hippocampus, and impaired the performance of exposed animals in tests of cognitive flexibility, working memory, and attention. These were not subtle statistical effects. They were dramatic functional impairments appearing within weeks of radiation exposure and persisting without recovery throughout the observation period, and the doses required to produce them were within the range that astronauts on a Mars mission would actually receive. But that was not the most troubling finding. What disturbed researchers even more was the mechanism. The radiation was not simply killing neurons, it was altering the signaling environment of the brain, disrupting the chemistry of synaptic transmission, reducing the density of dendritic spines on neurons, impairing the brain's own maintenance and repair systems. The damage was architectural, structural, the kind of change that does not easily reverse. What does this mean for a crew on a 2 to 3 year Mars mission? It means that the astronauts most exposed to GCRs during the transit phases could arrive at Mars with measurably impaired decision-making, reduced working memory, and altered emotional regulation, precisely the cognitive faculties most critical for managing the complex, high-stakes challenges of operating on the Martian surface far from any possibility of rescue. That is not the full story, not even close. Because radiation, as devastating as it is only the beginning of deep space's assault on human physiology. Remove gravity. That simple act, the removal of the one physical constant that every cell in the human body has been shaped by over billions of years of evolution, initiates a cascade of physiological changes that begins within hours and does not stop for the duration of exposure. Microgravity. The term sounds benign, clinically neutral. The reality is a full system biological restructuring that touches every major organ system in the human body, often in ways that amplify and interact with each other in unpredictable and dangerous combinations. Begin with the cardiovascular system. On Earth, the heart is perpetually fighting gravity, pumping blood upward against a hydrostatic pressure gradient that acts to pool fluid in the lower extremities and reduce venous return to the heart. The cardiovascular system has evolved an elaborate set of compensatory mechanisms: vascular tone, autonomic reflexes, the architecture of the venous system, specifically to maintain adequate circulation in an upright body in a gravitational field. In microgravity, all of this changes. Fluid shifts toward the upper body and head, producing the characteristic puffy face, bird legs appearance of astronauts in their first days aboard the ISS. A visual manifestation of the roughly 2 litres of fluid that migrate from the lower to the upper body within the first 24 hours. Blood volume decreases as the body's fluid-regulating systems interpret the fluid shift as a signal of excess volume and respond by suppressing thirst and increasing urinary output. Total plasma volume falls by 10 to 15% within the first week. The heart, suddenly freed from the need to pump against gravity and receiving less venous return from now-drained lower extremities, begins to atrophy. Cardiac mass decreases. The left ventricle, the main pumping chamber, loses muscle tissue in a process of disuse atrophy, fundamentally similar to what happens to any muscle deprived of mechanical load. The heart becomes smaller, weaker, and less efficient over the course of a long mission. When the astronaut returns to Earth and gravity reasserts itself, the atrophied cardiovascular system is suddenly required to perform its original function, and it cannot. Orthostatic intolerance, the technical term for the inability to maintain adequate blood pressure when standing upright, is nearly universal among returning long-duration astronauts. Some cannot stand without fainting for days or weeks after return. After a 6-month ISS mission, full cardiovascular recovery takes months. For a Mars mission crew arriving at the Martian surface after 6 to 9 months of microgravity transit, even at Mars's 38% of Earth's surface gravity, this cardiovascular deconditioning is a serious operational risk. The first hours and days on the Martian surface, when the crew is most needed to perform critical surface operations, are precisely the period when cardiovascular performance is most compromised. Now here's where it gets truly strange. In 2019, NASA-funded researchers studying astronaut Scott Kelly, who completed a 1-year mission aboard the ISS from March 2015 to March 2016, as part of the twin study with his identical twin brother and fellow astronaut Mark Kelly, published findings that went beyond cardiovascular changes and cognitive impairment into territory that was genuinely unprecedented. Scott Kelly's gene expression had changed. Not his DNA sequence, his underlying genetic code remained intact. But the patterns of gene expression, which genes were active, which were suppressed, how loudly various cellular programs were running, shifted measurably during the mission, and in some cases did not fully return to pre-flight baseline even 27 months after his return to Earth. The published analysis, led by a consortium of researchers across a dozen institutions and published in the journal Science in April 2019, identified changes in gene expression related to immune function, DNA repair, bone metabolism, and oxygen management. Telomere length, the protective caps on the ends of chromosomes that shorten with age and cellular stress, actually increased during Kelly's time in space, defying expectations. But then, after return to Earth, telomeres shortened more rapidly than normal, suggesting a complex and still incompletely understood interaction between the space environment and the cellular aging machinery. Cognitive performance testing, conducted throughout the mission and into the post-flight recovery period, showed that Scott Kelly's scores on certain tests declined during the mission and did not return to pre-flight baseline within the study's post-return monitoring window. Mark Kelly, ground-based throughout, showed no comparable changes. This means the space environment, the combination of microgravity, radiation, isolation, altered sleep cycles, and other factors, leaves biological traces that persist well beyond the mission itself. Not all of them are negative, not all are fully understood. But the demonstration that long-duration spaceflight alters human biology at the level of gene expression adds a dimension to the survival problem that no spacecraft engineer can solve with improved materials or better propulsion. The problem is human. The biology itself is not adapted for this environment, and the environment does not negotiate. Bone loss compounds the cardiovascular and cognitive challenges. Without the mechanical loading that gravity provides, the constant compression that bones experience simply from supporting the body's weight, the cells responsible for building new bone tissue, osteoblasts, reduce their activity, while the cells responsible for breaking down old bone tissue, osteoclasts, maintain or increase theirs. The net result is progressive bone loss at rates of approximately 1 to 2% per month in the spine and hip, weight-bearing regions where the effect is most severe. Over a 6-month ISS mission, astronauts can lose 10 to 15% of bone density in the lower spine and hip. Full recovery after return to Earth takes months to years, and for some astronauts, full recovery never occurs. The pre-flight bone density is never restored. For a 3-year Mars mission, the cumulative bone loss, even with aggressive countermeasure exercise, could compromise skeletal integrity to a degree that significantly increases fracture risk during the physically demanding activities of Martian surface operations. Current countermeasures aboard the ISS, 2 to 2.5 hours of daily exercise on specialized equipment including resistive devices, treadmills and stationary bicycles, reduce but do not eliminate bone and muscle loss. The exercise regimen itself consumes a significant fraction of the crew's working day and adds substantial mass and volume requirements to spacecraft design. And research suggests that even optimal exercise cannot fully compensate for the absence of gravity-induced mechanical loading in the long term. Muscle loss parallels bone loss. Skeletal muscle, like bone, requires mechanical loading to maintain its mass and function. In microgravity, postural muscles, the muscles of the spine, hip and lower extremities that are continuously active in a gravitational field simply to maintain upright posture, lose their primary load immediately. Muscle atrophy begins within days. Without aggressive countermeasures, astronauts on long-duration missions can lose 20 to 30% of their lower body muscle mass over 6 months. The interaction between muscle loss, bone loss and cardiovascular deconditioning creates a compounding problem. Weaker muscles exert less mechanical load on bones, accelerating bone loss. Reduced cardiovascular capacity limits the intensity and effectiveness of exercise countermeasures. The systems degrade in concert, each decline making the others harder to compensate for. And then there is the immune system. Research has consistently shown that spaceflight dysregulates immune function in multiple directions simultaneously. Some components of the immune response become suppressed. Astronauts show increased susceptibility to certain infections and elevated rates of reactivation of dormant herpes viruses, including Epstein-Barr virus, varicella-zoster virus, and cytomegalovirus. These viruses, carried by the majority of adults, are normally held in check by immune surveillance. In the space environment, that surveillance falters. Other components of the immune system become overactive. Elevated markers of systemic inflammation appear in astronaut blood work, reflecting a chronic low-grade inflammatory state that persists throughout long-duration missions. This chronic inflammation is not just a symptom, it is itself a driver of multiple other pathologies, It accelerates bone loss, contributes to cardiovascular dysfunction, and creates a neuroinflammatory environment in the brain that, combined with direct radiation effects, compounds cognitive impairment. The immune dysregulation has a particularly concerning implication for deep space: the complete isolation from medical intervention. Aboard the ISS, a medical emergency can be addressed by evacuation. A crew member can return to Earth within hours via a Soyuz or Crew Dragon spacecraft. On a Mars transit or on the Martian surface, that option does not exist. Any medical crisis must be managed with onboard resources and telemedical support. And for the 6 to 20 minutes, one way, that communications take to travel between Earth and Mars, depending on orbital positions, real-time consultation is not possible. A crew member experiencing a medical emergency during a Mars mission is, in a meaningful sense, alone. Let us pause for a moment and consider what this really means. 3 astronauts, or 4 or 6 depending on mission architecture, isolated in a spacecraft roughly the size of a studio apartment, receiving radiation doses that progressively impair their cognition and increase their cancer risk, experiencing bone loss and muscle atrophy and cardiovascular deconditioning, managing dysregulated immune systems that make them more vulnerable to infection and inflammation. They are also, simultaneously, navigating the psychological challenges of prolonged confinement, isolation, and the knowledge that no rescue is possible. Distance does something to the human mind that proximity-based experience cannot prepare you for. Human psychological experiments in isolation have been conducted in various forms: Antarctic overwintering stations, submarine deployments, extended cave isolation studies, and specifically in the context of spaceflight, the Mars 500 project conducted from 2010 to 2011 in Moscow, in which 6 volunteers spent 520 days in a sealed facility simulating a Mars mission. The psychological findings were instructive and sobering. All 6 participants remained physically healthy. But behavioral analysis revealed significant increases in sedentary behavior as the mission progressed, disrupted sleep-wake cycles despite stable lighting conditions, emerging signs of psychological withdrawal, and reduced motivation, and, most critically for mission safety, a deterioration in team cohesion and communication dynamics that, in a real mission, could compromise crew coordination during high-stress operational periods. The implications of this discovery are almost too vast to comprehend. Radiation and microgravity degrade the body. Isolation and confinement degrade the mind. And in deep space, both processes operate simultaneously, continuously, and with limited ability to intervene. The human being sent to Mars is not the same human being who arrives. There is a concept in human factors engineering called performance decrement under accumulated stress, the well-documented tendency for human cognitive and physical performance to degrade, sometimes catastrophically, when multiple stressors operate simultaneously over extended periods. In aviation, it manifests as crew resource management failures. In medicine, it shows up as diagnostic errors by fatigued clinicians. In high-stakes industrial settings, it underlies a disproportionate fraction of major accidents. In deep space, the accumulated stressors are not occasional or situational. They are continuous, environmental, and biological. They cannot be removed. They cannot be paused. They cannot be fully compensated by any combination of countermeasures currently available. And this is the finding that changes everything. When NASA and allied space agencies began compiling the comprehensive physiological and psychological data from long-duration ISS missions in the early 2000s, the missions of Valery Polyakov, 437 days, 1994 to 1995, Sergei Avdeyev, 379 days, 1998 to 1999, and the wave of 6-month increment missions that followed. The individual findings were concerning but manageable. Cardiovascular deconditioning, addressable with countermeasures. Bone loss, partially addressable with resistive exercise. Radiation, within occupational limits for ISS missions. Psychological stress, manageable with crew selection, training, and ground support. The cumulative picture, however, is something else entirely. In 2022, NASA's Human Research Program, the division responsible for characterizing and mitigating health risks to astronauts, released its most comprehensive risk assessment to date for a crewed Mars mission. The The report, synthesizing decades of research across more than 30 identified health risk categories, arrived at a conclusion that the space agency has communicated carefully, in measured language, without dramatic fanfare, but which, read directly, is alarming. A 3-year Mars mission using current technology and countermeasures exceeds acceptable risk thresholds in multiple, independent risk categories simultaneously, not marginally, substantially. Radiation. Mission dose likely to exceed NASA career exposure limits for some crew members, with significant probability of long-term cancer morbidity. Behavioral health. Extended isolation exceeds the demonstrated psychological tolerance duration without mission-threatening crew behavioral issues. Nutrition. Current food system technology cannot maintain crew nutritional status for 3 years without significant degradation of food quality and palatability, creating caloric deficiency risks. Vision. A substantial fraction of long-duration astronauts experience vision changes associated with increased intracranial pressure, a syndrome called spaceflight-associated neuroocular syndrome, or SANS, whose mechanism remains incompletely understood and whose long-term consequences over a 3-year mission are unknown. Let us address SANS specifically, because it represents one of the most unexpected and medically significant discoveries in the history of human spaceflight. Beginning around 2005, NASA flight surgeons began noticing something unusual in the post-flight medical examinations of long-duration astronauts. A significant fraction, ultimately found to be approximately 40% of astronauts who had spent 6 or more months in microgravity, showed structural changes in their eyes when examined with ophthalmic imaging tools. The optic disc, the point where the optic nerve enters the eye, was swollen, a finding called papilledema that in clinical medicine is typically a serious warning sign of elevated intracranial pressure. The eyeball itself had been flattened, its shape had changed, the posterior pole of the eye pushed in slightly, and the refractive properties of the eye had shifted in some cases by enough to require new prescription glasses. These were not subtle imaging findings. They were significant anatomical changes in a critical sensory organ, and the mechanism was not immediately clear. The leading explanation, developed through the work of astronaut physician Noah Malperin at the University of Miami and subsequently examined by researchers across multiple institutions, involves the cephalad fluid shift we discussed earlier. In microgravity, cerebrospinal fluid, the clear fluid that surrounds and cushions the brain and spinal cord, redistributes toward the head, increasing pressure within the skull. This elevated intracranial pressure is transmitted to the optic nerve sheaths, the protective tubes of tissue surrounding the optic nerves as they travel from the eye to the brain, and presses on the back of the eye from behind. Over months of exposure to this elevated pressure, the eye's structure remodels. The optic disc swells, the posterior pole flattens. The optic nerve sheath itself may show kinking or tortuosity, visual in MRI scans as a wavy, distorted appearance where the nerve should be straight. For most astronauts, these changes are present but do not significantly impair vision or mission performance during the flight. Some astronauts require updated corrective lens prescriptions. A smaller number experience vision changes significant enough to be operationally relevant. For all of them, the structural changes raise a question that has not yet been answered. What happens to eyes and optic nerves exposed to this elevated pressure, not for 6 months, but for 3 years? No human has experienced that. The mouse models provide some alarming suggestions, progressive optic nerve damage accumulating over time, but the translation from rodent biology to human ophthalmology is imperfect. The honest answer is that we do not know what SANS does to vision over a 3-year mission, and vision is not peripheral to mission success. It is essential to every operational task a crew member performs. The cardiovascular picture over 3 years is similarly uncharted in human subjects. The longest single spaceflight in history is Valery Polyakov's 437-day mission aboard the Mir space station in 1994 to 1995. And while Polyakov returned ambulatory and in remarkable condition given the duration, his mission was before the era of comprehensive physiological monitoring that characterizes modern research. The data from that era was sparse by current standards. Frank Rubio's 371-day ISS mission, completed in September 2023, represents the longest American spaceflight to date. His post-flight medical data is currently being analysed. What emerges from that analysis will significantly inform our understanding of what prolonged spaceflight does to the cardiovascular and musculoskeletal systems at durations approaching but still not reaching a Mars mission's length. But the fundamental challenge extends beyond the physiological findings of any individual mission. It involves something deeper and more difficult to engineer around. Evolution designed the human body for one planet. Not in any purposive sense, evolution has no purposes, but in the functional sense that every system in the human body reflects the selection pressures of 3.8 billion years of life on Earth. The orientation of our semicircular canals for detecting motion in a gravitational field, the architecture of our cardiovascular system for pumping against gravity, the calcium metabolism of our bones for supporting mechanical loads in 1G, the DNA repair systems calibrated for the radiation environment of Earth's surface, the circadian rhythms entrained to a 24-hour day. None of these systems were designed with flexibility toward the space environment. They are not easily adjusted. They are not modifiable by training or medication or engineering in the timescales relevant to a 3-year mission. They are the constraints imposed by 4 billion years of Earth-specific evolution, and they cannot be negotiated with. Some might wonder whether pharmaceutical interventions can bridge the gap, whether drugs designed to simulate the effects of gravity loading, or radioprotective agents to reduce radiation damage, or pharmacological countermeasures for SANS, can make the difference. The research is active and promising in some areas. Bisphosphonate drugs that inhibit osteoclast activity have shown some effectiveness in reducing bone loss. Anti-inflammatory compounds may partially mitigate radiation-induced neuroinflammation. Research into radioprotective drugs, compounds that either scavenge free radicals produced by radiation or enhance DNA repair mechanisms, is ongoing at multiple institutions. But no pharmaceutical countermeasure currently exists that adequately addresses the GCR problem. The physics of high-energy particle interactions with biological tissue produces DNA double-strand breaks, oxidative stress, and inflammatory cascades through mechanisms that are not easily intercepted by any available drug. You cannot medicate your way past a galactic cosmic ray. The only genuine solutions to GCR exposure are distance and time, neither of which a Mars mission crew can control, or shielding material in sufficient quantity to provide meaningful dose reduction, and here the engineering constraints become brutal. To reduce GCR dose by a factor of 2 during transit would require approximately 15 to 20 grams of shielding material per square centimetre of spacecraft surface, the equivalent in water of roughly 15 to 20 centimetres of water surrounding the entire crew habitat. For a reasonably sized crew module, the total mass of this shielding runs to hundreds of metric tons. Current launch technology cannot place hundreds of metric tons of spacecraft into Mars trajectory orbit at any cost that approaches feasibility. The shielding solution that would actually work is, by current technological constraints, inaccessible. This is the hard wall. This is the real reason no one has gone to Mars yet. Not the propulsion, not the navigation, not the life support, not the landing technology. Those problems are difficult but tractable. The radiation biology problem is a hard constraint that current physics and biology do not provide an adequate solution to, and the clock is not neutral. Every year of delay is a year of additional research, but it is also a year in which the case for human Mars exploration, relative to robotic alternatives, becomes harder to make on pure scientific grounds. Robotic missions do not get cancer. They do not experience bone loss or cardiovascular deconditioning or psychological isolation. They do not develop SANS. They explore indefinitely at costs and risks that make the human mission look, from a certain perspective, like an extraordinarily expensive way to put a person in a place they cannot safely be. The counter-argument, the human counter-argument, is real and important and worth stating directly. Human explorers adapt, improvise, and respond to unexpected situations in ways that current robotics cannot replicate. A geologist on the Martian surface can identify scientifically interesting features and decide to investigate them in real time, without waiting minutes for commands from Earth. A human crew can perform complex repairs and maintenance operations that robotic systems cannot. The scientific return of human surface operations per unit time substantially exceeds what rovers can achieve. But that argument about scientific return must be weighed against the probability that the humans performing those operations are doing so with compromised cognition, degraded cardiovascular function, reduced bone integrity, and eyes that have been structurally remodeled by months of elevated intracranial pressure. The human advantage in adaptability is real, it is also not unlimited. And the space environment is systematically eroding it throughout the mission. But this raises an even bigger question, one that moves beyond the specifics of Mars missions and into the fundamental relationship between human biology and the cosmos. Is deep space survival possible at all? Not in the engineering sense of keeping a spacecraft functional, but in the biological sense of maintaining a human being, cognitively intact, physically functional, psychologically coherent, across the timescales and distances that meaningful deep space exploration requires? The honest answer, based on current science, is that we do not know. And not knowing is a different thing from knowing it's impossible. The history of medicine is a history of problems that appeared impossible until they were solved. Consider the candidates for eventual solutions. Artificial gravity, generating a centripetal force equivalent to gravity by rotating the spacecraft or a portion of it, is the most obvious engineering response to microgravity's physiological effects. In a rotating habitat, the effective gravity experienced by occupants is determined by the rotation rate and the radius of the rotation. At a radius of 50 meters and a rotation rate of approximately 3 revolutions per minute, a centripetal acceleration equivalent to Earth gravity could be generated. Astronauts working, sleeping, and exercising in this environment would not experience microgravity's effects on the cardiovascular system, bones, or muscles. They would maintain Earth-normal physiology throughout the transit. The engineering challenges are real. A rotating habitat of 50-meter radius is substantially larger and more complex than any spacecraft humanity has built. The transition between rotating and non-rotating sections of the spacecraft, necessary for operations in microgravity, creates engineering complexity. The Coriolis forces experienced during head movements in a slowly rotating environment can cause disorientation and nausea, though research suggests this is adaptation-dependent and manageable at rotation rates below about 3 to 4 revolutions per minute. But artificial gravity does not solve the radiation problem. A rotating spacecraft is not a magnetically shielded spacecraft. GCRs penetrate regardless of what the crew experiences gravitationally. And the combination of artificial gravity, which solves the microgravity physiology problem, with adequate radiation shielding, which requires enormous mass, creates a spacecraft so large and massive that current launch technology cannot build it in any economically plausible time frame. Propulsion is therefore a limiting factor, not just for transit time, but for the entire architectural feasibility of a survivable Mars mission. Faster transit means less time in the radiation environment. A transit of 45 days instead of 180 reduces radiation exposure by 3/4, potentially bringing the total mission dose within acceptable limits even without comprehensive shielding, and a smaller, faster spacecraft requires less radiation shielding for a given mission dose target, because the exposure duration is shorter. Nuclear thermal propulsion, a technology demonstrated in ground tests in the United States in the 1960s under the NERVA program, and currently being revisited by NASA and Department of Defense programs, can achieve specific impulses roughly twice that of chemical rockets, enabling faster transits for the same propellant mass. Nuclear electric propulsion, using a nuclear reactor to generate electrical power that drives ion thrusters, can achieve even higher specific impulses but at lower thrust levels, requiring longer acceleration periods. Fusion propulsion, if achievable, could enable transits of weeks rather than months, potentially solving the radiation exposure problem by sheer speed. These are not purely speculative technologies. Nuclear thermal propulsion is engineering, not physics. The basic nuclear thermal concept is validated. The challenge is funding, political will, and the regulatory environment for launching nuclear systems into space. These are solvable problems. They require political and institutional commitment rather than new scientific discoveries. Beyond propulsion and shielding, the most radical proposed solution to the deep space survival problem involves not engineering the spacecraft around human biology, but engineering human biology for space. Biotechnology is advancing at a pace that makes proposals that sounded like science fiction a decade ago worth serious scientific discussion today. Radioprotective gene therapies, modifications to the DNA repair machinery, that enhance the speed and fidelity of double-strand break repair after radiation exposure are being explored as potential countermeasures. Research at NASA's Ames Research Center and at academic institutions including Stanford and Harvard has identified genes in extremely radiation-resistant organisms, including the remarkable bacterium Deinococcus radiodurans, which can survive radiation doses 1,000 times lethal for humans by operating extraordinarily efficient DNA repair systems as potential sources of insight for enhancing human radioresistance. Gene expression modification, rather than permanent genomic alteration, represents a more near-term possibility. If gene therapy or pharmacological means could upregulate the expression of DNA repair enzymes in astronaut tissues during the radiation-intensive transit phases of a mission, the biological consequences of GCR exposure could potentially be reduced without requiring the impossible mass of physical shielding. Similarly, research into synthetic biology approaches to bone maintenance, compounds or treatments that maintain osteoblast activity in the absence of mechanical loading, could reduce or eliminate the bone loss problem without requiring the mass and power overhead of a rotating habitat. None of these solutions are ready for human application in a spaceflight context. Many are at early research stages. The regulatory path to human testing, particularly for genetic or gene expression modifications, is long and uncertain. But the direction of travel is clear. The solutions to deep space survival are likely to come not only from engineering, but from biology, from our growing ability to understand and ultimately modify the biological systems that make deep space lethal. This raises a profound question about what a Mars mission crew would actually be, and what it would mean. If the astronauts of a future Mars mission have received gene therapies to enhance their radiation resistance, pharmacological interventions to maintain their bone density and cardiovascular function, and behavioral and nutritional regimens calibrated by AI-driven health monitoring to optimize their physiological status throughout the mission, at what point does the mission stop being an exploration of what human beings can do, and become an exploration of what engineered human beings can do? This is not an abstract philosophical question. It is the concrete frontier of the emerging field of human enhancement, the deliberate modification of human biological capacities beyond their natural range. And spaceflight is, in a real sense, going to drive this field forward faster than any other application, because no other human endeavour creates such stark and unambiguous biological necessity for enhancement. The history of exploration is a history of technology expanding human capability beyond its biological limits. Warm clothing for cold environments, diving apparatus for underwater environments, pressure suits for high-altitude environments. The astronaut suit is, at its core, a technology that creates a portable analogue of the Earth environment around a human body that cannot survive without it. Enhancement technologies for deep space survival are extensions of this same principle. Portable, biological analogues of the Earth environment, implemented not in hardware but in biochemistry and gene expression. The philosophical discomfort this generates is worth acknowledging, but it does not change the physics of galactic cosmic rays or the biology of bone remodeling in microgravity. The universe does not adjust its lethality to match human moral preferences. If humans are going to survive in deep space, human biology is going to have to change. The question is whether that change happens through technology applied externally, better spacecraft, better shielding, faster propulsion, or through technology applied internally to the biology itself. Almost certainly the answer is both. The survivable deep space mission of the future will be characterized by a partnership between advanced spacecraft engineering and advanced biological countermeasures that does not yet fully exist. And in that partnership lies something genuinely inspiring. The same species that evolved on a small rocky planet, protected by a magnetic field and an atmosphere, that first looked up at the night sky with nothing more sophisticated than naked eyes. That species is now, deliberately and systematically, identifying the specific biological obstacles that stand between itself and the cosmos, and working toward their solutions. That project is incomplete. The obstacles are real. The timelines are uncertain. But the project is underway. We began with a statement designed to unsettle, that we do not know how to keep a human being alive long enough to reach Mars and return safely. That statement is still true, but having followed the biology and the physics through their full depth, through radiation and microgravity, through bone loss and cardiovascular deconditioning, through SANs and immune dysregulation, and the psychological weight of isolation in a void. The statement is no longer simply alarming. It is the precise description of a defined problem, and defined problems in science and engineering are the ones that get solved. The human body is not designed for deep space. That is not a deficiency. It is simply the fact of having evolved on one particular planet under one particular set of conditions. Every organism on Earth faces the same constraint. We're all local. We're all Earth adapted. The difference is that we are the first species in the planet's history to consciously recognize that constraint and systematically work to overcome it. The ISS has given us 20 years of data. The twin study gave us a molecular-level portrait of what spaceflight does to human gene expression. SANS research has revealed an entirely unexpected mechanism of physiological change that is now the subject of targeted investigation. The Human Research Program has mapped 30-plus distinct health risk categories with greater specificity than any previous generation possessed. We're not stumbling into the problem of deep space survival. We are characterizing it precisely with the intention of solving it. One thread remains genuinely unresolved, and it is not a minor one. The galactic cosmic ray problem does not have an adequate engineering solution within current or near-term technology. The physics of high-energy particle interactions with biological tissue cannot be fully addressed by shielding, not at any spacecraft mass that current or foreseeable launch systems can deliver. The solution, when it comes, will require either a propulsion breakthrough that radically reduces transit time, a biological countermeasure that makes tissue more resilient to GCR damage, or an insight that is not yet in anyone's research pipeline. That open question is not a reason for despair, it is a specification. The universe has handed us a precise problem statement, written in the language of particle physics and radiation biology. Our task is to answer it. As we continue to develop the technologies and treatments that will eventually make deep space traversable, as each mission to the ISS adds another data point, as each Mars flyby adds another measurement of the interplanetary radiation environment, as the biological sciences continue their rapid advance, the gap between where we are and where we need to be is narrowing. It is not closed, but it is narrowing, and the stars waiting on the other side of that gap are not going anywhere.